It's an absolute pleasure to introduce today's speaker, Mihaela van der Schaar. She's the John Humphrey Plummer Professor of Machine Learning, Artificial Intelligence and Medicine at the University of Cambridge. She's a fellow of the Alan Turing Institute in London and a Chancellor's Professor at UCLA. She almost has too many accomplishments and honors to mention, but I will try to do my best. She was elected IEEE Fellow in 2009, and she has received numerous awards, including the Owen Prize on Preventative Medicine from the University of Cambridge, a National Science Foundation Career Award, 3 IBM Faculty Awards, the IBM Exploratory Stream Analytics Innovation Award, the Philips Make a Difference Award, and several Best Paper Awards, including the IEEE Darlington Award. In 2019, she was identified by the National Endowment for Science, Technology and the Arts as the most cited female AI researcher in the UK. Finally, she was also elected as a 2019 Star in Computer Networking and Communications by N-Square Women. So, with a great pleasure and without further ado, let's hear from Mihaela. The title of her talk is AutoML and Interpretability, Powering the Machine Learning Revolution in Healthcare.
Thank you very much for this invitation. So I'm Mihaela van der Schaar, and today I'm going to tell you about how AutoML and interpretable machine learning can power the machine learning revolution in healthcare. I do believe that machine learning can revolutionize healthcare. It can do so by delivering precision medicine at the patient level, enabling us to understand the basis and trajectories of health and disease, as well as informing and improving clinical pathways, enabling better utilization of resources, and allowing us to reduce the cost of healthcare. It can also transform population health and public health policy. An important ingredient in this agenda is the use of AutoML to develop clinical analytics at scale. But this is not enough. We need also interpretability. To truly empower the new human-machine learning ecosystem, interpretability needs to be added to AutoML. The research agenda of our group goes beyond these two topics that I'm going to describe here. It includes also time series forecasting, causal inference, reinforcement learning, inverse reinforcement learning, trustworthiness, as well as statistical machine learning, among others. If you want to learn more about our research beyond what I'm going to talk about today, please visit our lab website. Machine learning solutions in healthcare have been starting to emerge recently, and we have seen high predictive accuracy for some diseases. Also, the methods are data-driven and require few assumptions. However, there are many machine learning models to choose from. They require hyperparameter optimization, model selection, and hence extensive expertise in data science, which may not be available to clinicians, medical researchers, and others in the healthcare domain that want to use these machine learning methods. To understand this better, let us consider the following example. We have here 4 different clinical data sets with different characteristics, all in cardiovascular disease. And what you can see is that we have no free lunch. Different machine learning methods are best for these different data sets. Also, their performance improvement as opposed to the best clinical score or a statistical method such as Cox proportional hazard model may vary depending on the different data sets. So there is no one-size-fits-all machine learning solution for healthcare. What we would like is, ideally to predict in advance for a new data set, a new clinical data set, which machine learning model is best. And we would like to do that with confidence. We would like also to understand whether by aggregating together multiple machine learning models, for instance, using ensemble methods, we can do even better. And when we are talking about performance metrics, we may want to go beyond just area under receiver operating curve, which is what is shown here, into precision recall and also other metrics of performance, since in clinical settings, the data is often imbalanced and other metrics of performance may be more relevant. So how to really solve this problem? We have many diseases, many variables. There are different needs, and this is all changing over time as the different classes of patients are changing over time. the technology and the treatments to deal with these diseases is changing over time. A brute force selection of machine learning methods and associated design parameters would be prohibitively expensive, and as I mentioned before, would require extensive expertise in data science, which may not always be available. So instead, we are letting automated machine learning models to do the crafting of the machine learning models themselves. So, of course, we have heard in this series different types of talks about AutoML. So a key question I'd like to answer is, what is different in healthcare? First, we are going beyond just classification or regression problems. We are interested, as I'm going to show to you, in time-to-event analysis, survival analysis, competing risks, time series forecasts, as well as causal inference. All of this will need to be solved using AutoML. Also, there are other challenges associating with developing clinical analytics with the use of AutoML for the sake of healthcare. Healthcare data is biased by clinical practice. Also, no experimentation is possible. We cannot go in the wild and collect more data. We need to learn on the basis of whatever clinical data we have available. Also, the data is unstructured. Often there is a lot of missing information, and this may be even informative missingness. We need to integrate variety of data, from multimodal data, high-dimensional data, to develop this clinical analytics. In other cases, the problem may be even worse. The data may simply not be available due to privacy issues. Also, there are challenges that we need to overcome from a model point of view. As I mentioned before, there is no one-size-fits-all solution. Hence, AutoML needs to determine which machine learning model to choose. In addition, to integrate this in clinical decision-making, we need interpretability and explainability, trustworthiness, as well as reproducible machine learning. Let me start with the first and simplest of problems, the problem of automating risk prediction models in healthcare. Currently, when a patient is going to their clinician, for instance, their general practitioner, 1 or 2 risk scores are provided for this particular patient. Maybe a risk of cardiovascular disease and potentially for one specific type of cancer. However, what we would like to move towards is a setting where a clinician can get a holistic view of the patient health, and multiple risk scores can be provided to the clinician for many clinical conditions. Not 1, not 2, but a large variety. However, this is challenging and would require optimizing over a huge design space. And as I mentioned before, we don't only have a prediction problem. We also need to do data imputation and potentially dimensionality reduction. So even for a simple prediction problem, this is a challenging task. We have addressed this problem in 2018 in an ICML paper we call Autoprognosis, where we built a tool, an automated machine learning tool for crafting clinical scores. Autoprognosis takes clinical data and builds entire pipelines for prediction. Missing data imputation, feature processing, classification, and calibration. Depending on what particular algorithm is at a particular stage in the pipeline, what algorithm it is best at the previous or next step in the pipeline may change. So this is a complicated problem. In addition, as I mentioned before, we issue with Autoprognosis not only predictions, but also explanations. I'm going to talk about that later in my talk. Also, since the clinical data sets may be limited in size, we may want to learn from other complementary cohorts with the help of meta-learning, and Autoprognosis enables us to do that. In order to solve such a problem, we need to do a complicated optimization problem to build such pipelines. We need to determine at each stage of the pipeline which algorithm to choose, what hyperparameters for this algorithm should be chosen, and what pipelines we should be choosing. This is all a complicated optimization problem, a combinatorial optimization problem. But it is even worse than that. it is a hard learning problem because the utility function associated with these different choices is not known in advance. It needs to be learned for a new data set. So what we need to solve is a hard learning and optimization problem. The solution is well known. It is Bayesian optimization. But it is also well known that Bayesian optimization does not work well when we have many dimensions over which we need to optimize. And in the clinical setting, since we have entire pipelines, we need to optimize over hundreds, potentially thousands of dimensions. And hence, we need to deal with the curse of dimensionality. And as I mentioned before, Bayesian optimization is known not to work well in such settings. So what we did in our paper and in our work in autoprognosis, we used a structured kernel learning. The key idea behind this is simple. Some algorithms are correlated for a particular data set. And here by correlation, I mean that they have similar performance for this data set. And some are not. It is only the algorithms that have a similar performance for a particular data set that need to be sharing information and need to be jointly optimized. The other ones do not, thereby enabling us to deal with the curse of dimensionality. So what we are in effect solving is a sparse additive Bayesian optimization where we only optimize algorithms that need to share information. In this way, we are improving significantly the learning speed. But in order to be able to do that and learn which algorithms are correlated and which one are not, we need to learn online for a new data. And the structure of this kernel is unknown. So what we have is we have different appartenance of different modeling choices to different subsets. And then at runtime, we are learning using a hierarchical Bayesian method how to identify which algorithms are clustered together. We do that by putting priors on the decompositions using a Dirichlet multinomial distribution. And then as new data is gathered about the performance of these methods, we are computing the posterior decompositions and learn, for instance, that, for instance, XGBoost and Random Forest are in the same subspace, but maybe a particular multilayer perceptron is not. After we have learned all that, we are now able to construct pipelines. But we are not only issuing prediction on the basis of one pipeline. We use ensembles. And the reason behind that is that we would like to have also uncertainty estimates with respect to each pipeline. So we know its performance as well. In this way, we are also preventing information loss because using a simple pipeline may discard useful information from other pipelines. How do we build ensembles? Using Bayesian model averaging, where we are now creating an ensemble using the posterior distribution of the performance, and we weigh each pipeline based on its empirical probability of it being the best. We have used autoprognosis in a variety of settings, in cardiovascular disease, cystic fibrosis, all types of cancers, and more recently in COVID-19. Here is where the strength of AutoML can come into play. Just after a few weeks after the pandemic started in the UK, we were able to join forces with NHS Digital to build a decision support tool for hospital managers that was forecasting the upcoming demand for ICU resources. The reason we were able to do that so fast is because we were having at our disposal AutoML tools such as autoprognosis. If you want to read more about our research in this area and other projects we are having in COVID-19, please visit our website dedicated to these types of projects. But as I mentioned before, we are moving beyond prediction in the clinical setting. Let me describe to you the setting of survival analysis. Here, the focus is not only to predict whether somebody is going to die or not from a particular disease, but also how this probability is changing over time. So we do time to event analysis. survival analysis. This is a more challenging problem than the prediction problem I described before. And the reason is there is no best survival model for all survival horizons, as you can see in this example. I have different types of Bayes learners, and at different times, different methods are best. This is also highlighted here. You can see a variety of machine learning methods as well as statistical methods, and you see that their performance metric, highlighted here as the time dependency index, varies at different time horizons. So the desiderata is to build an automated machine learning model that enables us to construct a valid survival functions that has better discriminative performance than any individual model and is well calibrated. So what we are doing now, we are doing AutoML for survival analysis, and we build ensembles over these different time horizons. We want to have not only good performance as represented by the discrimination performance, which is here captured by time dependency index, but we also want to have good calibration as captured by time-dependent Brier score. This becomes, hence, a constraint Bayesian optimization, which is more complex than the prediction problem that I described in autoprognosis. It is a constraint optimization. And the way we are going to solve that is by quilting a pattern of survival functions. Let me show to you why we call this a survival quilt. We have here 3 different types of statistical and machine learning models for survival analysis, which are quilted together, meaning they are weighted together with different weights at different time points. And in this way, we are creating this quilting pattern, this temporal quilting pattern. This is an ensemble method which weights at different times these different Bayes survival methods with different weights. Also, as you can see here, and I'm going to just briefly highlight later, the quilting patterns are changing not at predetermined time points, but rather at endogenously determined time points. So survival quilts learns when is the best time to change the quilting pattern, thereby adapting the weights of the Bayes learners. Let me describe just very briefly the different steps involved in building survival quilts. The first step is temporal quilting, where we are constructing valid survival functions for a given set of weights, a quilting pattern, for different survival models over time. Because we want to have a valid monotonic risk function, the risk predictions at past time horizons are carried forward to future time horizons to provide a consistent risk function. Then, in a second step that I'm going to highlight next, we are solving the quilting pattern through a constraint Bayesian optimization. And finally, the quilting pattern is made robust through time horizon splitting, where we are determining endogenously when is the right time to change the quilting pattern. The second step, as I mentioned, is an involved one, because now we no longer have just a simple black box optimization problem like in the case of autoprognosis. We have now a constraint Bayesian optimization where we need now to learn both the utility function as well as the constraint. So both the discrimination, the discriminative objective, as well as the constraint, which is the calibration constraint, need to be optimized. So the constraint Bayesian optimizations has 2 GP priors now. We can turn this constraint optimization problem into an augmented Lagrangian Bayesian optimization with GP priors. However, unlike conventional Lagrangian optimization techniques that we are familiar with, because we are having now a learning and optimization problem being intertwined, this is a lot more challenging. Just to highlight the different issues involved, let me highlight here what is happening over time. As we are determining and computing the different Bayesian optimization iterations, we have plotted on the y-axis the augmented Lagrangian objective function. And what you can see is that after a certain number of iterations, we have found objective that is minimizing what we are interested in, but the constraint on the Brier score, on the calibration, is not fulfilled. So it is only the third time that this constraint is satisfied, and hence we can declare success and identify the survival quilt associated with it. If we are able to do so, we are able to use AutoML through its incarnation, survival quilts, to select the best survival model over time. Survival quilts is able to quilt the best model for the data, and you see here 3 different data sets from 3 different clinical domains, where indeed survival quilt leads to the best performance. It is capable to find the best model. Also, as I'm briefly showing in this slide, we are not only issuing predictions on the basis of endogenous time points, but rather endogenous time points. And survival quilts is able to select the best time to change the quilting pattern. And you can indeed see that endogenous survival quilts have superior performance as opposed to survival quilts where the timing of changing the quilt, hence the weighing of the different base models, is predetermined. Let me now go one step further and talk about treatment effects. It is well known that, for instance, as a patient, Bob, is diagnosed with a particular disease, and clinicians need to decide on what treatment is best for Bob. They need to deal with a very challenging problem because the treatment effects are often heterogeneous. So here is where machine learning can help, because it can help estimate the effect of a treatment or an intervention on an individual, thereby providing an estimate of what is the best treatment for the patient at hand. This is a complicated causal effect inference problem. And the reason this is challenging is that we do not observe in this setting counterfactuals. Let me describe this a little bit better. So I have here a training set where different patients are either treated or untreated. W1 means that the patient was treated. W is equal to 0 means the patient was not treated. We observe what happened to the patient given the treatment assignment, but we do not observe what would have happened if the patient would have been not treated or treated. We do not observe the outcomes of counterfactuals. We do not know what would have happened if the clinician would have acted differently. So we need to be able to learn in the absence of counterfactuals. This is no longer a simple standard supervised learning problem. It is a causal inference problem. And we need to be able to learn despite the absence of explicit labels. Hence, machine learning in general, and AutoML in particular, cannot use supervised cross-validation to select the best model. An additional problem that I'm not going to describe here, but which also needs to be overcome when we do causal effect inference, is that of dealing with selection bias. Because clinicians are not treating patients by closing their eyes and doing a randomized controlled trial. They have their own biases and knowledge, which lead to biases in the data set. So we need to also learn in the presence of such biases. Of causal inference is a very active area of research. Many researchers have contributed new causal models in a variety of machine learning venues. What you see here is just a summary of some of the main algorithms in causal modeling over the last couple of years. And you see some of the algorithms having an arrow. These are algorithms that were developed in our own lab. And the challenge now becomes which model to select for a new observational study. We would like again to empower clinicians and medical researchers with an automated machine learning tool, which is able to select for a new observational data set the best causal model that they can use for their study to build analytics. And again, the challenge is that we cannot select easily the best model because we cannot do cross-validation due to the absence of counterfactuals. This is a problem that we have solved in ICML 2019. So the way in which we solve this, and just to highlight one more time the challenge, is that in order to compute the model's performance for a new data set, we would like to compute the mean square error of a causal model. We want to compute what is known in the causal inference literature as PEHE, or precision in estimating heterogeneous effects. We would like to learn what is really the mean square error of this causal model. And again, we cannot do that because we do not have in our observational data set counterfactuals. The way in which we solve this is based on the following insight, which comes from high school algebra. It comes from Taylor series approximation. We know from good old Taylor series approximation that we can estimate the value of a function at a given input x1 based on its value at a proximal point, x0. In a similar way, in an analogy with this Taylor series, we can estimate and approximate the performance of a causal inference model as a functional of the data-generated distribution. So while we do not know the true distribution at theta 1, we can use synthetic distribution with known counterfactuals. For that, we use functional calculus. We use von Mises expansion. A distributional analogy of the Taylor expansion is possible in this way. And we are going to replace the derivatives which we are using in the Taylor expansion with influence functions. In this way, we can predict the performance of the causal inference model using influence functions of its loss on a similar synthetic data set. What we do in effect is we synthesize counterfactuals. And we do that in two steps. The first step is a plug-in estimation, where we are using a plug-in model, and then on the basis of this, we compute the plug-in PEHE loss, precision estimating heterogeneous effects. Also, we are doing as a second step bias correction. To summarize, we are estimating a causal model's performance through this type of first-order Taylor approximation. And what we are computing is the estimate for the inaccessible empirical measure. So this is not possible to determine because we do not have counterfactuals, but we are able to approximate it based on accessible empirical measures through this two-step procedure, in which we first estimate the synthetic distribution, and then we are estimating the derivative through the influence function. Now that we are having this at our disposal, we are able to estimate the performance of causal models. So for that, we have used 77 benchmark datasets for causal inference from the Atlantic competition. What you can see in this table is that there is no method that is best for all datasets. And even the best performing model at the time, 2019, which came from our group, NSGP, was only the winner for 17% of the datasets. What AutoML can do, empowered by influence functions, is to select the best model. And now in 72% of the datasets, we are able to select the model which leads to the best performance. So now AutoML can empower clinicians and medical researchers to select the best causal model for a new dataset. If you want to read more about this work on AutoML for causal inference, or for the many other models we are building on causal inference, our group is very active in there of causal inference, please take a look at our website dedicated to causal inference. Let me now go one step further and talk about the time series setting. As a patient is actually progressing through a particular disease, we would like to issue subsequent forecasts about different events of interest that may happen to this patient over time. And doing that is challenging as well. If it is to use time series models, a lot of challenges occur when applied to time series clinical datasets. For instance, the researcher will need to determine what type of RNN to choose, what type of architecture, whether to use attention or not, whether they should use long or short-term memory. And this is challenging because time series clinical data sets are highly non-stationary. The risk factors may be changing over time. We may have a lot of temporal distribution shifts. And hence, the best model for each time step may differ. And that requires a lot of expertise. So what we do in order to solve this using AutoML and empower clinicians with an AutoML tool that enables them to craft clinical time series forecast is through this new AutoML method that we have built, which we call stepwise model selection. This is presented in a recent AI Stats paper. And the solution behind this is a novel Bayesian optimization algorithm that is able to tackle model selection in the time series setting. At every moment in time in this time series setting, we need to have a new estimation of the predictive model. So we are treating the performance at each time step as its own black box function. So one could say that a way to solve this would be to define this as a multi-objective Bayesian optimization, where again, at every moment in time, the objective is the model performance at that specific time step. But such a multi-objective Bayesian optimization would be extremely complex and expensive, impossibly to solve. So hence, a solution that may come to mind to solve such a complex problem is to cast this as a multitask Bayesian optimization. This has quite some appeal because now we can transfer knowledge gained from previous optimizations at previous time step to new tasks to the current as well as subsequent time steps. So this may sound appealing and provides us some warm start, but has also disadvantages because it requires evaluating deep learning models on large data sets, which is prohibitively expensive, and it requires solving T separate Bayesian procedures in a sequence, all the way up to time T, in order to issue a prediction. And it is unclear how to allocate the evaluations of these different Bayesian optimization functions across these different subproblems. Moreover, such a solution does not take full advantage of information from all acquisition functions. So a solution that we are proposing in here to efficiently and jointly solve this multiple objective problem is to use and learn a deep kernel learning. So what we have built is a stepwise model selection via deep kernel learning. This key idea is to build feature maps that are measure the similarities between the different time series models at the different moments in time. How do we do that? As a first step, we are creating an embedding matrix, for instance, using an RNN. And then as a second step, we are obtaining a permutation invariant embedding using deep sets. The reason we need a permutation invariant embedding is because we need independence on how the different individual rows are ordered in the time series setting. Then, as the final step, we are generating the final feature map by taking this permutation invariant embedding and turning into a feature map with the help of a multi-layer perceptron. How well does this do? As opposed to machine learning models that are crafted by experts, so sophisticated RNNs where models are crafted by experts and hyperparameters are optimized carefully, our AutoML solution, which is out of the box, is automatic and simple, is able to use only standard RNN models rather than sophisticated ones, and yet it achieves comparable or better performance. This is all wonderful, but how can we turn these machine learning models into actionable analytics? For that, we need risk score understanding, transparency, we need to avoid implicit bias, we need to enable the clinical users to distill insights and new knowledge from the learned model, thereby making new discoveries. And we also need to communicate effectively how trustworthy these models are, such that the clinician knows what the machine learning model knows and what it doesn't know, when it is confident in its predictions and when it is not. There are many kinds of interpretations. Some are based on global feature importance, some on local feature importance. Some are looking at model nonlinearity, some at feature interactions. And most interpretive models, most methods for interpretable machine learning are good at just one of these. But the reality is that we need a whole variety of interpretations. Also, we need interpretability that is model independent, that is general, rather than tailored to only specific types of models, and which is post hoc. So we need to take any black box model and be able to interpret it. The interpretability should not interfere with the model training, which may introduce bias and compromise accuracy. Let us look at the first type of interpretability. I have here Mary, and I would like to issue a prediction for her upon diagnosis of COVID-19 from dying from COVID-19. I can use a black box model such as autoprognosis to issue this prediction. But then I would like to know why this prediction has been made. For that, one can look at what features are important when issuing this prediction. This can represent one type of interpretability. And this is what exactly our methodology called InVase in ICLR 2019 is doing. It is learning what features are important for this black box model when issuing this prediction for Mary. And you can see that for Mary, it is age and hypertension that have led to this prediction. However, for another patient, for instance, Bob, it could be that other features matter, 4 different features matter, rather than the 2 that I described here. So the number and type of features may change depending on the patient. How does InVase determine which features are important for a particular predictive model? It does so in an elegant way using reinforcement learning. Actually, we are using a very simple form of reinforcement learning to do so, an actor-critic framework. Let me tell you how this is working. So InVase is taking a black box model, such as a neural network or autoprognosis, and tries to learn with the help of an actor what features are important. The actor will select actions, which are in this case, which features are important for this particular model as believed by the actor. These are the actions chosen. Then the critic is taking these selected features and issuing predictions solely on the basis of the selected features. An error is then computed by the critic between the predictive performance of such a model that just uses the specific selected features as opposed to the original black box model that contains all the features. If the error in the prediction is low, it means that the reward of the actor is high, and this is communicated to the actor that then learns that the selection was correct. Conversely, if this error is large, the reward is low, and the actor will need to learn to identify the correct features for the current patient. This is a relatively complex problem where we are trying to determine through the selector function what features are the ones that are leading to this particular prediction performance. We can turn this optimization problem into an unconstrained optimization problem. But as in the previous case, this is not just an optimization problem, it's a learning problem as well, because we do not have access to the density required in order to solve this optimization problem. They need to be learned online. And this is challenging, especially in the case where we have many features. This is a problem that we have solved in our ICLR 2019 paper, and if you are interested, please take a look. What I'd like to instead highlight is the fact that InVase, unlike learning to explain, LIME, SHAP, and other models, is not only doing individualized feature importance, it is going one step further by being able to discover the number of relevant features that are important. So unlike these other methods, we are able to identify that these 2 features are important for Mary, but rather these 4 other features, or the same features plus 2 more, are needed for Bob. So it is the number as well as the type of features that are determined, and Invase is able to do that. So are we done? No, we are not done, because we do not want to have just this type of interpretations. We may want to identify the model nonlinearity or the statistical interaction between features. So what are we aiming for? We would like to have all of that. And more than that, in many settings in clinical environments, we need to produce a transparent risk equation to describe the black box model in order to have approval of this model in clinical practice guidelines. In addition, as I'm going to highlight later, different users of the model may want different explanations going beyond simple interpretability. So can we have it all? The answer is yes. In a NeoRIPS 2019 paper, we introduced a new idea that can demystify any black box model. And we are doing that using symbolic metamodels. Symbolic metamodels are able to take any black box model and turn it into a white box model that is represented by a transparent risk equation. What is a metamodel? A model of a model. And a symbolic metamodel outputs a transparent function describing the predictions of the black box model. An important advantage of such metamodeling is that we do not need to know what's in the black box model. I just need query access to the trained black box model. So the intellectual property of the black box model can stay intact. Symbolic metamodels then take these black box models, whether it's neural networks or autoprognosis or anything else, and project them into interpretable metamodel, a white box model. What type of metamodel space? This can be determined by a user. Some users may like polynomials. Some may want Bessel functions. It is the user that is determining what type of interpretability they want and what type of white box model they would like to see. How are we going to achieve that? We are doing that through a very powerful theorem, the Kolmogorov-Arnold theorem, which says that every multivariate continuous function can be written as a finite composition of simple functions, univariate continuous functions. Then we can take the black box model F, and we can learn an approximation of this black box model F through interpretable Bayesian functions J, and we can do hyperparameter optimization and learn what are these functions, these interpretable Bayesian functions that best approximate F in the interpretable space chosen by the user. What type of Bayesian functions we have selected in this paper? Meyer-G functions. I'm not going to go into the details of Meyer-G functions. They are contour integrals. But the reason we have selected them is because they can represent a very general class of functions. And simply through parameter selection of these Meyer-G functions, we can yield many familiar functions, polynomial, exponentials, etc. Then we are able to learn how to approximate the black box model in a very simple way. In an analogy on how we learn in a simple way a two-layer neural network and how we learn the weights of a two-layer neural network, similarly, we can learn the weights of a metamodel in a similar way through gradient descent. So the parameters of a Meyer-G function can be learned by gradient descent, and this can be done very fast. What can we obtain in this way? We can take a black box model such as autoprognosis and no longer issue predictions only on the basis of autoprognosis. You see here, for instance, that autoprognosis does a lot better than a Cox model in terms of area under receiver operating curves. But it is a black box model, which is not interpretable. With the help of metamodels, we are able to approximate autoprognosis and issue predictions with the help of an interpretable metamodel this time. And what you can see here is that the metamodel themselves, when applied directly on this particular data set, are issuing an interpretable and highly accurate model that it is only slightly less high performance than the black box model, the original black box model. What we have now is the ability to do everything we did before and more. Let me just give you a very brief example. We have here a meta model associated with a certain prediction, and we have risk equations such as this one that are enabling us to understand a particular prediction. Then, if we want to do individual level feature importance, we no longer need to do what we were doing with Invase, Lime, or SHAP, where we were just identifying a set of features that were important for this particular individual, for this particular black box model. Now we have a real equation, and this is going way beyond just individualized feature importance, because we are able to exactly capture how a particular variation or change, for instance, in BMI, will affect the prediction of risk. With this in our hand, we are now able to go beyond interpretability into explainability. What I call explainability is the ability to provide to different types of users, clinicians, researchers, of patients, different type of explanations depending on their interest. Whether it's for the clinician to determine why a predictive black box model recommended a particular treatment, or for a researcher why a data-induced hypothesis has been made. In this way, we are able to use meta models in a forward use to provide treatment justification, hypothesis induction, as well as variable interaction. And in the backwards use, by fixing, for instance, the reduced risk that we are interested in, we can see what features should somebody act upon to reduce this risk. This can be useful for dosage recommendation, for monitoring, for screening. So meta models are empowering us to do all this type of analysis. If you are interested in hearing more about this topic, inclusively a discussion of me and several clinicians, please take a look at my Turing talk from April 14th, which is on YouTube. Also, we have gone since then beyond just symbolic meta models. So if you are interested in the latest work we have done in this area, please take a look at our interpretability work, which has been just accepted for NeurIPS 2020. In addition to interpretability, we also want trustworthiness. And for that, we want to go beyond just Bayesian approaches based on Monte Carlo dropout or deep ensembles. The reason this is not enough is because we would like post hoc measures of trustworthiness. We do not want to interfere with the model. We want to train the model and then understand post hoc how trustworthy they are. In addition, we also want to have true coverage guarantees. This is necessary for machine learning in healthcare. In a recent set of 2 papers just accepted and published in ICML 2020, we were able to do that. Discriminative jackknife is providing post hoc trustworthiness and with coverage guarantees. This can be applied on top of any static black box model. And for the time series setting, we were able to issue again post hoc frequentist uncertainty estimates for recurrent neural networks, and we are able to do that through a new idea from blockwise influence functions. I hope that this talk will give you a feel about the excitement of using machine learning to empower clinicians to make better decisions by providing them with tools not to replace them, but rather augment their decision-making through actionable intelligence that machine learning can offer. In addition, clinical researchers can be empowered with data-induced hypotheses, and this can integrate not only clinical data, but also omics data. Finally, pharmaceutical industry can be empowered through machine learning-driven data-induced causal discovery. So I hope you can join us in this revolution. I would like to end by acknowledging my brilliant students and postdocs on the basis of which this entire presentation has been made. So their work has been key in all this that I presented here. And if you'd like to get in touch or learn more about our research, please visit our website dedicated to automated machine learning. Thank you.